Okay, so I guess we should start because today we are starting a very important topic. And this topic, especially if you, yes, give me a second. If you pay attention to it from the beginning, you will be able to follow very easily, and in fact, it will explain many of the general concepts in programming. So I usually find it personally very interesting. But from my experience, many people, the first time they get introduced to that topic, they feel it's very hard. And the reason is not because it's hard, but because it follows a very sequential order of understanding. So if you really drop at one step, everything afterwards becomes very tough. So my suggestion is, especially, we said this already in previous topics of the course, but for this topic especially, which will continue with us, well, in fact, until the end of the course, but especially until the end of the C part, if you feel that there is any step, I will go very slowly, especially at the beginning. And if you feel that there is any step that you don't get, stop me and ask directly, right? Because we want to build it in a logical manner. And if we follow the flow we do in the lecture, I hope that you have a different feeling about pointers more than what most people think it's hard, okay? So please go ahead. Yeah, I will do this directly after, if you don't mind, okay? Because now it might take a few minutes. So another thing to say, yeah, please. Yeah, this is what I was going to say right now. So the midterm does not include pointers, okay? So the midterm is until the end of yesterday's lecture, which is strings, and it doesn't include pointers or anything that we discuss from now until the midterm time, okay? And I will ask the main TA to post an announcement about that. Good. Okay, great. So is there any other question before we start? This topic also will be covered along with almost all the topics until the end of the C part, which is including structures and dynamic memory allocation. This is what concerns lab 3, the last lab in the C part, right? So you will see a lot of, I would say, interrelationship between what we discuss in the lecture and what you will be doing in the lab. To make it a little bit easier for you, and I know that you have midterms, etc. So I already posted lab 3 today for those that might want to start giving it a look or take it a question by question. I know that we didn't cover all the topics yet, so it will take us some time to do that. But you can start, for example, after pointers, you can answer one question. After we go for dynamic memory allocation, you can do another question, etc. etc. Good. Is there any other question logistically or technically before we start? Okay, good. So before discussing pointers, there is something we need to understand fundamentally about programming and what happens in the hardware, regardless of the programming language, right? And this is one of the key aspects of C. It gives you the visibility that other languages like Python, for example, you have covered before, doesn't give you, right? So what happens in the background? We said that when you declare a variable, in fact, when this program is being executed, the hardware will go to the memory, allocate the memory that is needed, or the memory size, or basically the memory capacity that is needed to store that variable, right? And when we discuss different types, we said every type defines multiple things. Among them is what is the size required for that variable. For example, int, we said it might need 32 bytes. 32 bits, which is 4 bytes. Float might be 32. Double is 64. Characters is just only 1 byte or 8 bits, right? So by defining a type, you also define, you tell the hardware how much memory you need for that variable. Good. Another thing that we need to understand, and it's more aligns with hardware courses, digital design and com.org, is memory is byte addressable, right? But that's in fact something every programmer should know, right? So memory is byte addressable. What we mean by this is that every unique location in the memory, the programmer sees it has a distinct address, and this location only holds 1 byte, right? So if I look into the memory as a programmer, well, it's much more than this uniform view, but abstraction is useful, as we discussed before. So memory is much more complex in hardware. But from a software perspective, what you only see is a sequential I would say, locations or sequential spaces of memory or memory locations that are byte addressable. When I say byte addressable, it means that every single location has the width of 1 byte, and every location has an address. This is really what we mean by being byte addressable. This makes sense? Good. Great. So, and another maybe thing that we need as a background is that addresses by nature cannot be negative, right? That makes sense because I use the address. What is the purpose of an address in a computing system? I take the address, go to the memory, it gives me a certain location. So that's the index. You can think of it as similar to the index of an array, the index that tells you what memory location or what byte you want to access. And this cannot be negative, right? I cannot have a memory that has an address of a negative value, because that means, what does it mean? If I'm starting from address 0, incrementing, it has to be all the time positive, right? So addresses by default are positive values. Good. So as we said, if I define a variable called int n, given that this is an integer, I know that the hardware needs 4 bytes in the memory to store that n. And then later on, if I modify the value of n, what the hardware will do, it will go to that memory location that is used for storing n, take whatever value is there and modify it with the value of 4. Remember when we tried this out without initializing a variable and we printed what is in the memory, it was a garbage value, right? It was some value that from a previous program or somewhere else that we don't know. And when you overwrite a variable by doing this line, for example, it will go to that memory. So assume that this is my memory that is byte addressable. You go to one address and I want to store 4 bytes, which means, in fact, you allocate these 4 locations for your variable, right? Because we said every single location is 1 byte. So n will take all these 4 locations. And when you overwrite n, the hardware will go to that location, that address, and write 10 there, right? This is really what happens when these 2 lines get executed in your software. Does this make sense? Good. So far, things seems logical, seems easy, right? This is just a view of what really happens in the background. Another thing we have seen before, but didn't explain in a very detailed manner, is this AND operator. Do you remember when did we use this AND operator? When did we need it? Yep. Yeah, well, that's a very good thing that I wanted someone to say that. So first of all, thank you. But if you remember, for the Boolean AND, it was in fact 2 AND operators, right? So this is the logical AND. In C, it's 2 ANDs. Yeah. For scanf. Yeah, exactly. We use it for scanf. And the reason is, we said this is an indication that I'm passing this variable to be written by the function, right? So I want scanf. If you remember, there was something like this, scanf, and then I have a specifier like d, and then I'm passing a variable n. Why I'm using that? Because I want n to take the value from the console through scanf, so I want n to be modified. And by then, we call this might be called by reference, right? When you pass a variable by reference, and the purpose is you want the poly function to be able to modify your variable. So you pass it to be giving a right authentication, basically, right? So this is what we have discussed about the AND operator. But in fact, this is more or less like an abstract simple view. Now it's time to learn more about that. What the AND really means, it means the address of the variable. So you're not really passing the variable itself, but rather passing the address in the memory. Why does this achieve the function we said before? Because if you pass to scanf, let's say I already defined n as we had before in the previous slide, and this is the address of n. Let's say the address of n is something like F7 or anything, any value, right? Here I have the value n equal 10. If I'm passing to scanf, not the value of 10, but rather the address where n is being stored, that means scanf can use this address to go to that memory location and overwrite it. Right? This is how really passing a variable to be written happens in reality, right? If you look into that line, scanf, and then you pass that, what is happening is that this is not really I'm not passing the value of n. Instead, I am passing F7, which is the address where n is being stored. Why I'm doing this? passing this address to the function enables the scanf reading the value from the console and go to that memory location and overwrite n, right? This is how really overwriting happens. Good, please. Exactly, of n, yeah. Yeah, exactly. And this is why we called it passing by reference, because I'm passing the reference to n, right? It's memory location, right? So to enable the callee function to be able to modify it. So far, so good. This is why we call the AND the address operator, because if you use the AND in front of any variable, it gives you the address of that variable. And we'll try this right now on online GDB. Good. So if I have an example like this, so let's, in fact, you know what? Hopefully things doesn't, please go ahead. Yeah, go ahead.
So what's the type of this? Is like
yeah, this is what we will come to. So that's an excellent question. It's just a little bit advanced question. So wait for it. We will know in a second that this is in fact a pointer. So it has the type of so it has the type of a pointer to an int. So I will come into it. Just bear for a second. Okay, good. So if I just do this, what I'm doing right now is I'm simply defining a normal integer variable, n has a value of 6, and then I'm printing two different things. I'm printing the value of n itself by really passing n to the printf. And here I'm claiming that I'm printing the address or the memory location of n by passing the AND operator n. And here you see that I'm really using a different specifier, which is %p, which we didn't see before. %p is referring to an address because it's a pointer type, right? So I will come into it. So I will run, and let's see what do we get. So the memory location of n is some sort of an address in hexadecimal representation. This is the memory location in that machine where n is being stored, while inside this value, inside this address, n has the value of 6. So you see now how the AND gives you the address, not the variable itself. Does this make sense? Is there any question?
sorry, where's the memory?
Yeah, well, that's a good question. So this website is just a front-end interface, but they have server machines in the background that they have a GCC compiler that runs really that code, right? So there is a machine somewhere in the world that we don't know where.
Someone else's.
No, it's not my machine address. That's correct. Yeah, because this is just an online compiler that uses servers somewhere. Yeah, it's very similar to GitHub. When you submit your code to GitHub, there is the autograder. What really the autograder does, I have a Makefile script that they run in their own server machines, and then they just give you the result, right? So it's more like a cloud computing infrastructure. Good. So we have seen that already. Now we understand what is the AND operator. Every time I switch, I should do that. Okay. Good. So we understand the AND operator. And we have seen the specifier B that is in fact used to print an address. Good. So far things make sense, they are logical, and this is what we have seen. So if I want really to debug further the memory locations, we know that an integer has 4 bytes. So in fact, it's not a single address. It should really have 4 different locations in the memory, right? But the address that is given here, or in general, the address of any variable, is the address of the first byte of that variable. Because again, memory is sequential. So it goes in an incremental fashion of that addresses. So if I give you the address, if n is stored here in these 4 bytes, this is called the address of n, the address of the first byte of that variable, right? And then all of this would have the value of 6. Good. And as you can see here, addresses are incrementing in, you guys know hexadecimal, I assume by now. So addresses are incrementing by a value of 1, right? C, D, E, F. So every time the address increments by 1. Well, comes from this is that in fact I cannot use the address operator for an immediate value, right? Because if you remember, we cannot also do operations on an immediate variable, like assign, for example, 1934 equal X. This cannot happen because 1934 is immediate value. It's not stored in the memory. It doesn't have a memory location, which in sense means that you cannot use the address operator for, because address operator gives you the address in the memory. If this value is not stored in the memory, well, you cannot really use that, right? You cannot also do this in an expression, because again, an expression gives you an immediate value result. It's not a variable in the memory, so you cannot really use the AND operator for. Are we good? Is there any question? Yeah, please. Yeah, that's a very, very excellent question. So I would say generally no, right? And the reason is, and this is a little bit of a complex topic sometimes discussed in computer architecture courses, sometimes discussed in operating systems courses, that is called virtual memory. What really happens is that those addresses we see here are not the actual addresses that are used to index the memory in hardware, but instead for security reasons and different other reasons, there is a layer of translation that is happening, what we call virtual memory versus a physical memory. For example, in my machine here, I might only have 16 gigabytes of DRAM, right? But then I can in fact run any program that would require much more memory. For example, if you play gaming, usually gaming would require much more memory than 16 gigs. But you still will be able to run this program in your machine. How can you do this? Leveraging virtual memory. So virtual memory gives you the illusion that your application has infinite memory. And then in the background, it does some translations and caching, right? It's a very advanced topic, so don't worry about it right now. But the answer is generally, you cannot. But just to be completely correct, in some embedded systems, like Arduino, for example, if you have tried Arduino before, Arduino doesn't run operating systems by default, which means you have applications called bare metal. So you can write C code in Arduino that in fact takes a direct address. Why? Because there is no translation, no virtual to physical translation, which means I can address directly the physical address of the memory. Okay. Thank you. Are we good so far? Okay, so now we will build on that by understanding how those addresses kind of help us also understand how arrays happens in reality, right? So we discussed arrays before. We know how they work, but we can have a much better understanding if we really understand their addresses, right? So let's see this interesting example. So I define a very easy small array that has 3 entries, -1, -2, -3, and then I'm printing the address of every single element there, right? So if I run that and look into the addresses I get, here is the address of B0, the address of B1, address of B2. When we discussed arrays the first time, I told you that arrays, one of their main features is that they got allocated in the memory contiguously, right? In a sequential manner. So the addresses must be back to back, right? This is a main difference between arrays and lists in Python, for example, or any dynamic data structure that we'll discuss later on, linked lists, etc. That arrays must be back to back in the memory, contiguous basically, which means entries would have sequential addresses. But I never proved this, right? Because we didn't know about addresses and pointers before. So now is the time to show you that. If I'm looking into the address of B0, and put in mind that this is an integer array, okay? Because this will be related to a question I will ask right now. So I'm printing the address of B0, it gives me this address. I'm printing the address of B1, it gives me that address. I'm claiming that these two addresses are a proof that in fact arrays are contiguous in memory, but how does this happen? They are not really +1.
Since each integer is 4 bytes, The address for the first variable would be C, so that includes C, D, E, and F. So the address for the next one would be 0, 1, 2, 3. And the third one would be 4, 5, and 6.
Exactly. Thank you. So that's really what is happening here, is that every location is 4 bytes. So if I'm starting my array with this address, which is 0, well, basically all the numbers are the same except the last 2 digits. It's EC. C is basically 12, right? So I would have C, D, E, F. And then I'm done with the first 4 bytes of the integer. So I will move to B1, which is starting from 0. And I've incremented the digit afterwards from E to F. And then it will 0, 1, 2, 3. And then the third one will start from 4. So these addresses are sequential, but every single entry is taking 4 bytes. Does this make sense? Is there any question? So this helps us more understand really how arrays are being stored in the background, right? So I see it a bit useful, in fact. Okay, great. One thing to highlight here is because these addresses, so these addresses, here, for example, in that example, they are different. If I run online GDB again for exact same program, you might end up with different addresses. The reason is, well, the operating system will allocate your array to whatever memory it finds suitable, right? So not every time gets allocated to the same place, right? So here I'm assuming that the first location is allocated to 0, 0 thing. So the second one will be 0, 4, and the third one will be 0, 8. Good. Now, again, building on top of this, we still need to understand what is in fact the name of the array. When we also discussed arrays, we said it's a rule in C that I cannot really use the name of the array in any operations. Like, for example, if I have an array int A that has 3 elements, and then int B that also has 3 elements, I cannot write something like A equal B. We said that's not allowed in C. You cannot use the array name for doing such expressions. What is the reason for this? We didn't say it. We said it's rule in C, right? But in fact, also understanding addresses and pointers will help us understand this. Why that's the case? Because if we go back to our explanation of that 3 addresses you have here, and that's A0, that's A1, that's A2, and everyone has its own address. The array name itself, which is A, in fact, is the address of the first element of the array. This is called the address of the array, right? So if I want really to get A, which we'll try right now, you will find that A really is a pointer. It has a value of an address. So why you cannot really assign an address to another address, because now you are modifying the memory, which is not allowed, right? So the array name, what does it represent? Which is the question in this slide, is basically it represents the address of the first element of the array, right? And later on, we will see how we can really define arrays using pointers, because it's just simply an address. Good. Yeah, please.
How do you track of the type? Because like the number of bytes you have to skip depends on the type. So the name only should the address.
Yeah, because the name doesn't change. And this is another reason why you cannot modify your array name, like write something else into it. So it's always only the start. So the array name doesn't navigate, right? But I guess your question is that if I want to navigate the array using pointer, how can I really know how?
Say you want to access the second element, you have to skip some bytes, right?
Yeah.
And the number of bytes changes based on the type.
On the type, exactly.
So how do you keep track of the type?
That's a good question. We'll come into this as well. You will find that in fact we have pointers, pointer types corresponding to different types of variables. So by knowing that this is an integer pointer, you know that it's pointing to int, and that means you need to increase by 4. So it's, yeah, again, another advanced equation. Just wait for a second, I'll come into it. Yeah. Exactly. That's also another reason, is that in C, well, we showed that it has to be contiguous, and also it has to be, in fact, all of the same type, because you don't have a track of how much memory allocate. That's not a dynamic data structure. It cannot be of a different size. So every single entry must be of the same size, and hence must be of the same type. Exactly. Thank you. That's a good catch. So now let's go back to our online GDB and try to print also the array name, because I just made a claim and maybe we want to assess that. So the memory location, no, the memory location of B, maybe I just leave it as B. I will just write B here. And let's see what do we get. Well, if you look, this is an address that I really got out of B. But if you compare this one with the address of the first element, just exactly the same value, right? Which means B is in fact holding a pointer or an address to the first element. One thing else to observe is that when I tried to print B, I didn't use the AND operator. What is the reason? Why do I need to have use AND here but not here? Yeah. Exactly, thank you. So B0, what is the type of B0? It's an integer, right? If I want to print its address, I have to use the AND. But what is the type of B itself? It's an array, but now we know that what is its type? It's in fact an address, right? So it's a pointer. We'll know about this later on. So this is why I don't need the AND, because on its own, it's in fact an address. Time for questions. If there is any question, any confusion, please go ahead. Okay, good. So we have already discussed this, but again, understanding more about addresses can help us also understand it. Is we said C does not have array boundary checking, which means it allows you to access array elements outside of your scope of the array or your definition of the array or declaration. Why that's the case? Because the way this really happens in reality is that it does what we call pointer arithmetic or address arithmetic. What in fact it does is, where's my pen? Assume I have this B4 that has 0, 0 here, and then it has 3 and 4 here, and that's B. This is B0, we know that. This is B1, B2, B3. If I want to access something like B4, which is somewhere here, that is not part of the array, how the hardware is able to address it? In fact, when you index an array to access a specific element, what really happens in reality is the hardware will do the following. I have the address of the first element, which is B, correct? Which assume, for example, it's 0x0. Okay, I will take this B and add into it your index. Let's say I want to access the second element, 2. Multiply this by the number of bytes of each entry, which is in our case 4, because it's an array of ints. B plus 2 multiplied by 4 gives you what? Gives you 0x0 plus 8, which is the address of 0x8. If you think 0x8 is in reality the address of the second element, right? Because you start from 0, you jump 4, and then 8, right? So this is really how B of 2 is done by the hardware. Later on, we'll learn more about pointer arithmetic, but that's exactly what is happening in the background. Yeah, please. Exactly. And this takes us to what your friend here said is if I want to access the fourth element, the hardware will do exactly the same thing. It doesn't even care about what is the value of I. It will just say B plus whatever I you have, let's say it's 4. So it takes the address of 16 and it goes here all of a sudden. That's outside of the array boundary. I don't even check. I just do my pointer array. And that's one reason why that's not safe to do. Just grab it, exactly, or overwrite it, which is even worse, right? So we can even kind of extend this discussion and say even I, the index can be negative, because again, it's just a valid arithmetic operation. If I say B of -2, for example, what is going to happen is I would say B plus, now it's -2 multiplied by 4. But because I started from 0, that is not in fact a valid address, you get a segmentation fault. But if B, for example, had the address of 8, well, it's fine that 8 minus 8 is 0. 0 is a valid address. It just go there and grab what is there, right? So it also allows you to traverse on this opposite side. Make sense? Which is also not safe, definitely. Questions? Okay, so let's see it in reality then. So assume I want to access what? I pick a value 10, for example, something completely outside of our boundary. Well, I got the address. What did I do? Yeah, I got the address, which is for 10, but I wanted the value itself. I just want to see what is there. So let me see, also have the value. To print the value, I should use D. And here I remove the and, right? Do this, well, we got something there that we didn't write. It's something from another program, right? Good. If I did the negative thing, you'll find that also it jumps back. Did it run? Yeah, if you see it, it jumps back. So see that the first element we have is 9C, correct? While negative 10 is 7.4, which is less. So it goes back, right? And it gives you some value that is also random that we don't know. Good. Is it same one? Maybe they initialize everything to that value. I don't know. Let's see. Yeah, it's the same. That's interesting. Let's try another thing. 20. That's just different, right? So it depends really on what is being stored there. It's completely random. You cannot really tell. I believe you had that issue with Eclipse sometime, yeah. Right? So you really don't know what is happening there. Good. Is there any question? Okay, so I guess we are doing excellent progress there. We already know it, so we shouldn't really discuss about it. So all of this discussion about addressees takes us to this important topic. We have been talking about addressees a lot, printing them, looking into them, but there is no handful way of operating on them in many programming languages. One big advantage of C is allows you this control over the memory by having the type of a pointer. What is a pointer? Just think about it as a data type that allows you to interact with addressees. Pointers always hold addressees of other variables, right? So it's a data type. And this data type, if you recall, we said data type defines three main things, right? Well, I already have them on the screen, so I wouldn't ask. But simply, what are these three main things is how much memory you need for the variable, what are the valid values this variable can get, and the third one is what are the valid operations, right, that you can operate on this variable type. And pointer is exactly doing this. So what is the size? Well, it in fact depends on how much width you have for your addressees. Most of our modern machines are 64 bits. So you have your address as 64 bit. That's the width of that variable, or how much memory you need for it, which is 8 byte. What are the valid operations? Well, there is what we call address arithmetic, or pointer arithmetic. We'll discuss it in a bit of a detail right now, but we had an example of how to operate on an array. And also, what are these are the valid operations, and what else? The valid values, right? This only gets, because that's a pointer, it holds an address, it only gets 0 or positive values. It cannot get negative values. Good. And this takes us to also your friend question here, which is, how do I know, right? I have a pointer that holds an address, but my operations will depend on what I'm pointing to. If I'm pointing to, for example, to an array of int, I need to jump by 4. If I'm pointing to an array of character instead, I need to jump by 1. If I'm pointing to an array of double, I need to jump by 8. So the operations on the pointer will depend on the type you are pointing to. For that reason, this need kind of led to the invention of different pointer types based on what variable they are pointing to. So we have an integer pointer, which means it holds an address of an integer variable. We have a double pointer, we have a character pointer. So any type you have has its own corresponding pointer type, correct? And if we want to visualize the way we define pointers, we use this asterisk thing, right? So if you normally define a variable called n, and this is an int n, you can define a pointer by using the asterisk thing, and you call it, well, n pointer, for example, and this can have the address of n. So I use the asterisk operator, right, which we usually call also the dereferencing operator, but don't worry about this now. It's just, this is how you define a pointer. exactly as you define a normal variable, but just add the asterisk after the type. Good. So this is an example of how to define this, and it will help us really visualizing what does it really mean. If I'm defining a variable pointer to point to an end, what happens in reality is there is another variable here, n, for example, that is stored somewhere in the memory. It has this address, assume, right? And it has the value of 8. If I define n pointer to point to that by assigning the address of n, now we know that this is the address of n, by assigning it to that pointer, what we really do is we create a link, right? So what we say is I want n pointer to hold the address of n. What is the address of n? It's this value, right? So I want to store this in the n pointer variable. So what you really do is you create that link, which in a sense seems something like a link between that pointer and that variable. So the basic essence of a pointer, it's a memory location, but it has a special value, which is the address of another variable, right? So the pointer is a variable in its own, which means you need to store it somewhere, right? You need basically, this is where the pointer is being stored, in that address. But the actual value of the pointer, instead of being an int or a double or a normal variable, it's an address of another variable. That pointer itself. You guys are asking very excellent questions, advanced ones. So this takes us to the interesting topic of pointers to pointers. Because in reality, if we say that pointers are just normal variables, well, I can hold their address. Well, I can hold their address in another pointer. And then what about pointers of pointers of pointers, right? So you can really do all of this chain. And here comes what we call linked lists, for example. A linked list data structure is nothing other than nodes that are having addresses to other nodes. And those nodes themselves having a value and an address for another node, right? So you can create a chain, right? And that's in reality all how we can create that chain is we'll discuss this later on in a bit of a detail, but that's an excellent point, is that assume this is my memory view. And I have here one location and here another location and here another location. In this location, assume it's multiple bytes. I have an int variable. This n1 has an 8, and this has some address, right? Then I have a pointer here, which is this n pointer. And I want it to store n. So what I will do is I will take this value, write it here. So I'm creating that link. What you are saying is in reality, I can create another pointer. I call it pointer square for now. And then make it point here by taking that address, put it here. And I can keep doing that. So I create a list, a linked list, right? A chain, basically. Any other question, please? Yeah, you mean how much memory the pointer need? It's the width of the address, right? Because here I'm storing inside this pointer the address of that variable. But how long is that address? Usually in our machines, 64 bits. But for example, if you talk about Arduino, it's 8-bit only. For some other machines, 16 bits. So it depends on what is the width of the address that you can have in your machine. Right? Because what do you store? So the question is simple. How much memory do I need here? Well, an earlier question should be asked. What do you store here? If you store an address, then you should ask yourself, what is the maximum address width you can get? And then this should be your allocated memory. Right? Does this answer your question? Another question? Yeah.
So what happens to both the address of n before you assigned it, like the specific one, do both of them have the n value?
I guess what you meant is not the n value, but rather the n address, correct?
Right.
Yeah, correct. So the idea is that this address is somewhere in the memory, but you don't have track of it. You didn't store it somewhere, so you cannot access it from your code, right? But to be able to access it from your code, C allows you to really do this through pointers, right? For example, if you're using Java, Java doesn't have pointers. So in fact, I cannot really track that address and know what is its value. There is no way for me to really know where n is stored. But C, because it's lower level, it gives more control, then it allows you to store that value in a pointer and print it and work with it, right? So to answer your question directly, now this address is not in fact stored in two different places. It's only stored in that memory location. But here we've just had it as a value because what the hardware uses to really go into it, right? This makes sense?
Yeah.
Great, thank you. Any other question? How much time do we have left? Oh, how much time do we have left? You guys know? Oh, yeah, okay, thank you. So we have 5 minutes, that's good. So we have, okay, so we said we define pointers using this asterisk, right? And we have seen the AND operator. But one question might arise is, what if I have the pointer? So, well, in other words, now we are taking it in that flow. I have the variable, I take its address, point it in the pointer. But what if I have the pointer that's storing some other variable, and I want to get the value of that variable? Can we go from the, like here, we are going from N to pointer. Can I go from here to here? If I have access to N pointer, can I get the value of N? That's the question we try to answer, right? And this is answered by what we call the indirection operator. How to do this? I use the asterisk in front of the pointer name, and this now takes me to the value of the variable that N pointer is pointing to. Very complex statement. But the idea is, and N gives me the address of N, which is this value, right? Asterisk N pointer gives me the value of 8, which takes you in the other direction, right? So if we want to see that, let me see how I can quickly write this in our example here. So I can make this symbol by defining here. Okay, so assume I define a pointer. An int pointer. And I call it, well, my pointer, anything. And then I assign into it the address of B0, okay? So now the memory location of, too slow, of B0 has the address of that, which is, oh no, I cannot really bear that. So let me copy and reload. Okay, so has that, which is supposed be equal to that. And we will see what I mean by that here. So the first one is the normal address of B0, which we get through and B0. But the second one is I will get through my pointer. So what I'm printing right now is I'm printing the value of and B0, which is the address of B0, and the value of my pointer. We're expecting both to be the same, right? Because what I have done is I initialize my pointer to the address itself, right? I forget the quote here. No, I have it. Yeah, this is. Okay, so the B0 address is this one, while the pointer has this one. And as you can see, both are the same, right? So if you look into these two addresses here, right, they are completely identical. Good. So we know that now my pointer holds the address of B0. Good. So now assume I want to print the value of B0. I want to show you the dereferencing operator. So the value of B0 going to kill me. Okay, so the value of B0 is yes, we were talking about server machines, cloud computing, comes slow sometimes. Okay. Okay, so that's I want to bring the value of B0. I don't know if they are penalizing us for trying to tamper with their own memory locations or what, but yeah, we will see. Come on. Okay, so I will probably try something else. Or it's a problem on my own machine, might be, I don't know. It's already over. Okay, so well, maybe we don't run this example now, but I want to, let's stop. So basically what I wanted to show you is I can do two things. Maybe I show it on the slide, and Friday we can try it. So simply, what I wanted to print is I wanted to print n pointer and see what does it give me and compare it. Oh, it's my machine then. Okay. And compare it to B0 itself, right? The actual value. And what I'm claiming is that this asterisk thing should really give you the actual value. Here in this slide is the value of 8, which is n, right? Yeah. Exactly. It's going to overwrite n from 8 to 20, right? That's really what's going to happen, right? So let me see. Yeah. So this is exactly what's going to happen is you will take n, remove 8, overwrite it to 20. The way it works is the hardware will go to the n pointer, take the address, go to this memory location, overwrite it with the value, right? So the way we read the asterisk is the value of, right? So we read the value of the address of n pointer is supposed to be 20. Yeah, it will be 20. Yeah, because it's just you write in one location. You don't write in multiple locations. Yeah. So let's start from here next time then. Thanks, everyone.